Actually, we will be proving in generally. Generally, we have to prove this thing. I will not state first this theorem. Generally, what is our aim to prove? Our aim is to prove that if F is analytic on a domain D in C, and C is any contour, any I will write it as simple, not even simple. There will be just a closed. It's any closed contour in domain D, then we have to prove this thing, that the integral of this function, f analytic function, over any closed contour is 0. This is what will be our most general form of the Cauchy theorem. But to reach this milestone, we have to go stepwise. First, we will prove a theorem that I just stated, Cauchy-Goursat theorem for triangles. That means first I will take C to be a triangle. First I am going to take it to be a triangle. That if you have a domain D, then first we will prove this theorem when just a minute, I'm sorry. When this is a triangle, we will prove this theorem. And this will form our basis to reach this theorem that I just stated here. And second, after triangles, we will prove this this part type of theorem when D is a more special type of a domain, and when D is a simply connected domain. When D is a simply connected domain, and then we will be able to establish this fact that for arbitrary domain and any closed contour inside this, the integral of an analytic function is 0. So we begin with this Goursat theorem. Let me first write its statement here. Let f be an analytic function on a domain D, and D be a closed triangle, in D, then the integral of this function fz. See, when I am saying that I am taking this closed triangle, it means we have this domain, let it be a domain D, and let us take the triangle is something. When I say that triangle, it doesn't mean the triangle just its boundary. It means the anything that is inside these three line segments. Everything here between these three line segments. Just let me everything here, this thing. And when we say that closed means that including these boundary lines also. And then we have to find the integral, because since this is a line integral, for line integral you just need the contour, and the boundary of this triangle is a contour. It consists of three pieces, three sides. Then we have to prove that the integral there is 0. So what is the procedure? Let me first write the procedure how we are going to prove this theorem. first what you have to do, you have to choose the midpoints of the sides of this given triangle. You just choose the midpoints. Let's also give the vertices. Let Z1 be the vertex, Z2 and Z3 be the vertices of this given triangle T. This is triangle T, and let us choose its vertices. Midpoints M1, this be M2 and M3. Now what we have to do, we have to draw another triangle joining these midpoints. If you draw this another triangle, now how many triangles you have? You have 4 triangles here. Triangle T1, let it be something T2, T3 and T4. So let's first establish this here. Let Z1, Z2, Z3 be the vertices of the triangle T, and M1, M2, M3 be the midpoints of the segments Z1, Z2. This is the first side of this triangle, and M2 is the midpoint of the side made up of the segment Z2, Z3 and Z3, Z1 respectively. See. Now let's look at the distance of these midpoints from each other. Now M1 minus M2, this distance. What is M1? M1 is the midpoint of this line segment joining Z1 and Z2, so it has to be the sum of Z1 and Z2, and it's half. It has to be Z1 plus Z2 half, minus M2 is the midpoint of the line segment Z2, Z3. It has to be Z2 plus Z3 over 2. Simplify it, what you get, you just will have Z2 cancelled out. You will be having Z1 minus Z3 over half. That means the length of this side of the triangle, which is inscribed inside this bigger triangle, by joining the midpoints. This is the length M1 minus M2. The modulus of M1 minus M2 is the length of this side of this inner triangle, and this length is half of the length of the. This is half. Okay, this is half of the length of the line segment joining Z1 and Z2. Okay, because this is midpoint, that's why. So similarly, likewise, you have M2, M3. This length has to be equal to, if you compute this, M2 has to be Z2 minus Z1 half, and the length of the other side, which is has to be M3 minus M1. It has to be equal to Z3 minus Z1 half. So what we get from here, that the length of the smaller triangles, you have 4 triangles, length of the smaller triangles is actually half of the length of the bigger triangle, where K equals to 1, 2, 3. You have 4 triangles. So you can see here that length. What is the length? L is the length. How you find the length? We have given a method to find the length also, but here length means the perimeter of the triangle. So it has to be half of the bigger triangle. So let us note this fact here. We have to note other things also. Now put I equals to integral our triangle boundary of the triangle T of f of z dz. This is the integral that has to be shown to be 0, and also we define integral over each of the sub triangle, and we denote it by ik. Then by the properties of the line integrals, you can write down this I integral as sum of the four integrals ik, k from 1 to 4. See how you are able to do this thing. You have a triangle here. Let me change the color. Which color? I will use blue now. See, you are taking this direction of triangle T to integrate the function. You take the positive direction, that is the anti-clockwise direction. Now, when you write the integral over this bigger triangle as a sum of the integral over all the boundary of all these four triangles. So, what are the boundaries of these four triangles? Look at the boundary of the triangle T1. Boundary of the triangle T1 is the half of the sides Z1 M up to side M3 to Z1, and another is Z1 to M. But another side is also included. When we take the integral over boundary of the T1, we will have this side included also. That means this is also added in that sum. And similarly, when you take the integral over T2, you will have this side also being added. And say when you take the integral over T4, you will have this side also added. But again, also you take the integral over T3. When you take the integral over T3, look at the orientation now, because orientation has to be anti-clockwise. When the orientation is anti-clockwise, you will have direction in this way. You will have in this way. So when you take the integrals over all these four triangles and sum up those their integrals, when you get to see that the integration happens twice over the sides of this inner triangle. But what is the difference here? It happens in opposite directions. First it is from M1 to M2, then it is from M2 to M1. So what happens then? You know that when you change the orientation of a curve, then the sign of the integral changes. So first when you are integrating the integral from M1 to M2, the sign is positive, and when you are integrating from M2 to M1, same integral, the sign will be negative. So positive and negative, then both these terms will cancel out. That means the contribution of the integral over these sides or the contribution of the integral over the interior this triangle will cancel out, and so we will be left only with the contribution of integral on the sides of this bigger triangle. That's why we can write this integral as a sum of the integral over these four triangles. You got it, or you need some more explanation? Julian?
Got it, sir.
Okay. See, that means this thing is there. Summation k equals to 1 to 4 integral boundary of tk. It is f of z, tz. Let's give it some name. Let's call it, what do we call it? Let's call it first if we need to refer to it. Now, we claim that we show that for some k, out of these four values of k, there is some k for which you have this inequality here. We have this inequality here that the integral corresponding to that k is greater than or equal to modulus of the integral by 4, integral of this f over t upon 4. We have to prove this thing. So suppose this doesn't happen. For any k, you don't have this inequality. If you suppose, if you don't have this inequality for any value of k, then for if you have ik not greater than or equal to 1 by 4 of I, modulus of I, then you must have this 1 by 4 of mod of I for every k equals to 1, 2, 3, 4. So this implies that you take the sum over all these k's, you will have mod of ik, k from 1 to n is less than 1 by 4 summation k from k from 1 to 4, 4 mod of I. So what is this thing? Well, this is equal to mod of I. But the left hand side is I, because this is the sum, and because of the here what we wrote here, because of this equation first, that means if you don't actually, if you say that there is no k for which you have modulus of ik bigger than 1/4 of modulus of I, then you will get this thing, which is a contradiction. So hence there must be some k for which mod of ik is bigger than or equal to 1/4 of mod of I. Or equivalently, you must say that mod of I is less than or equal to 4 times mod of ik. We are going to have an important consequence here after here. So this is for some k, and suppose you, without loss of generality, we assume that there is only one case, one such k. And if you have more than one values of k for which you have this inequality, then what you are going to choose? You choose the least value of k and retain that. Now k corresponds to certain triangle. Suppose k corresponds to, suppose k is equal to 3. Then what you are going to do? You are going to repeat the same process what we did for t. What is the same process that you are going to repeat? You are again going to take the midpoints of this triangle that you found, let it be T3, and you are going to draw another triangle inside this triangle. And then again, inside T3, you will have 4 triangles. And then again, you will use the hypothesis. Then again, you will use the hypothesis that again you will prove that there exists at least one sub-triangle inside this big triangle T3 over which you have this inequality that we just proved, over which we have this inequality. We have this inequality. Is it okay? So now what I'm going to do, I'm going to relabel this triangle, relabel the triangle Tk for which you have this inequality as T1, signifying the first stage. Now what we are going to do, I'm going to repeat this process. It would be better to use the word argument. Repeat the above argument. Repeat the above argument for T1. And if we repeat the argument for this T1, we will get another triangle that will be denoted by, to get another subtriangle of T1, to get a subtriangle triangle of T1 as T2, for which we will have this I1. Let us denote the integral over this T1 as I sub 1. Where is my eraser? Denote this integral as I sub 1 is less than or equal to 4 times integral over this integral. So, and continue in this fashion, if we keep continuing this process, we get at nth step, we get a triangle Tn. I'm not using the brackets. Tn such that this Tn is contained inside the triangle Tn minus 1, and integral over this Tn minus 1, which I have given this notation, modulus of this is less than or equal to 4 times integral over triangle Tn. We are going to this. Not only this thing, also note that diameter of T1. What is the diameter? Let me go back to tell you what diameter of a triangle I am assuming to be the length of the longest side, because this is what the definition of diameter also says. It will be the length of the longest side. And you see the length of the longest side of the triangle T1, T2 and T4 is going to be less than or equal to the 1/2 of the length of the longest side of the triangle T. So what I'm going to diameter of T n is going to be less than or equal to 1/2 half of diameter of T. Thus, we obtain in this way a sequence, we obtain a nested sequence, I must say, nested sequence. Nested sequence means you have triangle T, let me call this triangle T to be T0, then inside it we obtain the triangle T1, and inside triangle T1 at second stage we obtain a triangle T2. In this way you have triangle Tn minus 1, you have triangle Tn, and in this way you can continue this process. Nested sequence this. It is a sequence of these triangles are closed triangles and they are bounded also, so this is a nested sequence of compact sets, because closed and bounded sets are compact sets such that so what is the diameter of Tn, which is less than or equal to 1/2 diameter of, it is not Tn, it is Tn minus 1. It is diameter of Tn minus 1. And if you keep applying the inequality over Tn minus 1, you will have less than Tn minus, this will be less than or equal to 1/2 whole square diameter of Tn minus 2, and so on. It will be less than or equal to 1/2 to power n diameter of T. And see, diameter of T is a fixed constant triangle. It's not going, its diameter is not going to change. And so if you take n to infinity, 1/2 n is going to 0 as n goes to infinity. So you have what? You have a nested sequence of compact sets, and all these compact sets are non-empty. And what's happening that their diameter tends to 0 as n goes to infinity. So you must be reminded of a very well-known theorem, which is the Cantor's intersection theorem. So all the hypotheses of Cantor intersection theorem are satisfied here. So therefore, by Cantor's intersection theorem, what is the conclusion? It says that the intersection of this nested sequence and from 0 to infinity, again I'm misusing the notation. I'm not using brackets with this. I'm just writing Tn. This is non-empty and it contains exactly one point. Contains exactly one point. Say that point is Z0. So Z0 is common to all these triangles. In particular, Z0 belongs to T also, and T is contained inside the domain D. So F is analytic at Z0. Now you have F is analytic at Z0. If F is analytic Z0, so F is differentiable also at Z0. So what it means to be differentiable function, I'm going to use that kind of definition that you used in several variables case of differentiability. And so uh, I'm going to write this in this way for given epsilon bigger than 0, there exists certain delta greater than 0 such that for z minus z naught less than delta, I can write this expression f of z is equal to f of z naught minus, not it is plus z minus z naught, the derivative of f at z naught, plus it is z minus z naught times e neta of z, where modulus of neta of z is less than epsilon for z minus z naught less than delta. You can just apply this. You can again get back the derivative from this linearization of this derivative. So you have this thing here. So what I'm going to do now, I'm going to integrate this our in nth triangle. This expression, integrate this our nth triangle, boundary of the nth triangle. What you are going to get, you are going to get this integral Tn f of z dz is equal to, if you simplify it, you will get it f of z integral over boundary of Tn f of z naught minus z naught derivative of f at z naught into dz plus, you just have to simplify it. What you have to do, you just take the f of z naught and z naught f prime z naught in a separate on one side, and you will be having z times f prime z naught left, and another term you will have separately is z minus z naught times neta of z. So you have now z times boundary of Tn z derivative of f at z naught dz plus it is integral over boundary of Tn, it is z minus z naught into neta z dz. So this is it. Now I can further simplify it in the first integral. I have integrand as a constant part, so I can bring it out f z naught z f prime z naught. You take it out and you just integrate it boundary of Tn dz. And in the second integral also, you can take out this f derivative at z naught. This is a constant quantity. You will be having integral over boundary of Tn z dz plus integral over boundary of Tn and z minus z naught eta of z dz. But look at the first two integrals. The first two integral here, this is an integral over closed contour. This is a closed contour. This is a boundary of a closed contour, and it's zero. It's zero. You just might have seen it from line integrals properties, and also integral over z dz. You just substitute its. Uh, you just integrate it over the triangle. It is also going to be zero. These are the integrals, elementary integrals that you must calculate by yourself, and you must have seen it in line integrals also. So these two values of these two integrals is zero. So I'm left with only one integral, and the integral is so we have this in, which is integral over boundary of Tn fz dz, which is equal to integral boundary of Tn z minus z naught eta z dz. Or I can further write is mod of in to be less than or equal to, because I can take in modulus inside and use this triangle inequality type thing for integrals, is mod of Tn mod of z minus z naught mod of eta z mod of dz. Let me call this thing star. Now what you have this setting when you have mod of z minus z naught to be less than z naught. Now when you say that z minus z naught is less than z naught, that means you're talking about a disk. You are talking about a disk of radius delta centered at z naught. Also, since you have that diameter of this triangle Tn is tending to 0. So if diameter is tending to 0, I can make diameter to be less than delta also. When I make diameter to be less than delta, what I can do, I can inscribe this triangle inside this disk, because once the length of the triangle is smaller than, so any triangle, because see z naught is z naught belongs to this point in this triangle Tn, because z naught is in the intersection. That's what we found through Cantor intersection theorem. So z naught will be inside this, and I can make a triangle, this triangle Tn, for sufficiently large n, so that this triangle lies inside this disk of radius delta. The only reason it lies here because this diameter tends to 0. So I can make smaller and smaller possible triangles to fit inside this disk. So we assume that this triangle is inside this disk, and now what you're going to do, what you are going to there, and since this triangle is inside this, and further now in equation star, if this triangle is inside this disk, and you have estimates for this. What are the estimates for this disk? Is that out this disk you have this neta z, modulus of this neta z is less than epsilon. So from star I will have this modulus of in to be less than epsilon, and I can make this z minus z naught to be less than maximum of z in this triangle boundary of Tn times mod of z minus z naught integral boundary of Tn, it is mod of dz. So, but what is this maximum? This maximum is nothing but, this maximum is the diameter of this triangle. This is the diameter of this triangle, and the part in under integral here is nothing but, this is the length of this triangle Tn. So the inequality that we have now is mod of nth integral, this is less than or equal to epsilon times diameter of triangle Tn dot length of triangle boundary of the triangle Tn. But we have the relation, we have a beautiful relation with the diameter of nth triangle Tn with the diameter of the triangle T. What is that? It is less than epsilon into, it is 1 by 2 to power n. It is diameter of T, and similar for length, I have length 1 by 2 to power n, length of triangle of T. Now, let us get back to this inequality. Yeah, where is this? Yeah, this one. We require this now. And if you look at this inequality, what is this inequality? Uh, this inequality is we have like this: n minus 1 is less than or equal to 4 times this one. If you keep successively implying, what you get mod of phi to be less than or equal to 4 to power n times mod of in. And from this above inequality here, we have this term to be less than or equal to uh, 4 to power n as it is, because you have the estimate for mod of in. It is epsilon times, you just simplify things here. You have 1 by 2 to power n, 1 by 2 to power n. That means you will have 1 to power 4 to 1 upon 4 to power n into, it is diameter of t times length of boundary of t. So you will have these terms cancelling each other, and what is left to you is that modulus of integral this is less than epsilon times, it is diameter of triangle t and length of triangle t. So that is integral over triangle of t mod z f of z dz, in its modulus is less than epsilon times diameter of t and length of t. And clearly, since epsilon is an arbitrary number, and if I take epsilon to 0, it goes to 0. Because here the diameter of t and length of t are constant quantities, they are not going to change. They are fixed numbers, so constant times anything goes to 0 is 0. So this gives us the required conclusion that we wanted to have. The integral of this analytic function of this triangle is 0. So this is the proof of this triangle. So I stop here for today, and this is a very important proof. You just go through it bit by bit, and the method, actually the method used to obtain this triangle is a very important method. And the why it is important is that it doesn't require the continuity. Note that the proof does not require the assumption that derivative of analytic function is continuous. If you remember in first unit, when I was talking about the partial converse of CR equations, in partial converse of CR equations, we required the hypothesis that the partial derivatives need to be continuous. That would imply that the derivative is continuous, and I had promised you to tell in coming chapters that exactly the partial derivatives are continuous, but we haven't reached there. We have proved this Cauchy theorem without using that assumption, the continuity of partial derivatives. But by using this Cauchy theorem, we will prove a Cauchy integral formula, and that will prove that the partial derivatives are continuous. But we have to wait for that. So I stop here. Do you have any questions I can take on? बोलिए. हम्म. बोलो.